first midterm practice exam, problem 7. It says find the magnetic field everywhere due to the surface current and find the force on each component of the loop and describe the loop's motion. To find the magnetic field, first thing I'm going to do is set up a coordinate system so that this will be a little bit easier for me. And so I'm going to set up my standard Cartesian coordinate system in right-handed XYZ coordinates. In this case, the current is flowing in the positive x direction. Now, in order to find the magnetic field everywhere, we're going to employ a Ampere's law, and we're going to take the Amperian loop that we like for surface current is actually a box. The box is going to be the height of the box here is going to be given by the, let's call that D, and the length of the box will be given by a capital L. Ampere's law says, the integral form of Ampere's law says that the current around any closed loop, the integral of the magnetic field around any closed loop is equal to the current enclosed in that loop. And so this is integral d2x n hat dot j. Now I haven't told you which way I'm going around this loop, and now I'm going to figure it out because I want this n hat and j to point in the same direction. So by right-hand rules, that means I'm going to be up on this side and down on that side. Now, for reasons of symmetry, I can argue that the magnetic field due to this current as a function of position is only going to depend upon the y coordinate, and it's only going to point in the z direction. So this is going to be bz, which will only be a function of y, k hat. Furthermore, for reasons of symmetry, I can argue that if this plane is at the y equals 0, I can argue that bz of negative y is minus bz of positive y. And so those are the two symmetries that we're going to use to find this. Now looking at this, this loop is going to have 4 components. I'm going to have one going up on the right-hand side, one going down on the left-hand side, and then I have 2 of them that go in the y direction. But I can see that my magnetic field points only in the z direction, so those 2 components pointing in the y direction because of this dot product are going to go away. So I only need to consider for this left-hand side the components going up and the component going down. Component going up, I'm going to get the length because the magnetic field is going to be constant. It doesn't depend on the z coordinate, it only depends on the y coordinate. And so it's going to give me the length, so that'll be L. The direction is in the positive k hat. We've just defined this here to be in the positive k hat, so this will give us 1 over mu naught bz as a function of y. On the other side, I'm going to get L. I have in the minus k hat direction, and so I'm going to get a minus sign, so this is going to give me minus 1 over mu naught. The bz of minus y, which, using this symmetry, I can combine these. This is going to give me 2L bz as a function of y divided by mu naught. For the right-hand side of this, I just need the current that's flowing through this. Well, that is simply going to be the surface current K times the length L. Surface current K times the length L. So setting these two equal to each other, I have 2L bz as a function of y divided by mu naught should be equal to the surface current K times L. Or I can find that the bz component as a function of y is simply mu naught K over 2. The L's are going to cancel. So it turns out to be somewhat independent of y. It's still actually a function of y because of this. If I were to write the vector component of the magnetic field, right, for any position, this is going to be plus mu naught k over 2, and this is in the k hat direction, in the z, positive z direction, for y greater than 0, and minus mu naught k over 2 k hat for y less than 0. And so now we have found the magnetic field everywhere for that surface current using Ampere's law. The next step is to find the force on this loop. So keep part of it. So the magnetic force is equal to this QV cross B. I'm going to replace this QV, right, with an integral d3x of rho. So d3x rho is essentially Q, and then V, cross B, but this rho V is simply the current density, and so the magnetic force is integral d3x J cross B. In order to get something that's a little bit easier to use for us, I'm going to use this realization that the integral d3x J can be broken apart as to an integral dl and an integral d2x J. This integral d2xj is going to be the current that goes through, so this is the I enclosed, and it has a direction given by the direction of j. Direction given by the j vector. So using that, I have to look at our picture again. The picture is going to give me that I have 4 pieces here. I have a piece where the current is in the positive I hat direction. I have a piece where it's in the negative I hat direction. I have a piece where it's in the negative k hat direction, and a piece where it's in the positive k hat direction. And so writing those out, I'm going to get the magnetic force is going to be equal to this integral dl. This is going to give me the current, and then I have these directions. I'm going to go ahead and write down my magnetic field. My magnetic field is always going to be mu naught k over 2, and then the current that I am going to get out of this, right, is, or the directions that I'm going to get out of this, I have 4 of them. I'm going to have I hat, I'm going to have minus k hat, I'm going to have minus I hat, I'm going to have positive k hat. And these will all be crossed with the k hat vector from the magnetic field. I can see that these two are going to go to 0, and so I'm only going to get a force on the top portion and the bottom portion of this. And in fact, the force is going to be in opposite directions, because I hat cross k hat is minus j hat, while minus I hat cross k hat, of course, is in positive j hat. And so I'm going to find that the magnetic force, the size of this loop is size A, and so this integral dl is just going to give A. So this is mu naught k I A over 2 in the minus or positive j hat direction. And so this is for the top, and this is for the bottom part. So the total force, of course, is 0. So if you add the force from both of them, this is going to be 0. So F total is going to be 0. But that doesn't mean this thing isn't going to move. What this says, right, is the motion that this loop is going to experience is it's going to experience a torque. And it's going to experience a torque about the x-axis. And so it's going to try and rotate in counterclockwise direction about the x-axis. So this is going to rotate counterclockwise about the I hat direction. So that's it.